This chart compares the total insured value of a single hyperscale data center against the maximum capacity of the global insurance market. While one site can be valued at $30 billion, the market covers a fraction of that, roughly $2.5 billion. This capacity gap is localized in specific geographic clusters. Hyperscale campuses aggregate in narrow zones, like Northern Virginia or Dublin, meaning a single regional event can threaten multiple tens of billions in assets simultaneously. For an actuary, total economic loss equals 5 layers: property damage, business interruption, SLA liabilities, cyber recovery, and third-party claims. Traditional models assume business interruption requires property damage, but here, SLA and cyber lockdowns trigger massive financial losses without physical equipment breaking. Treating digital infrastructure like 20th century commercial property ignores this decoupling. It leaves catastrophic liabilities stranded and completely unpriced. The operation of a hyperscale facility relies on the constant, real-time interaction between electrical power, thermal regulation, and cyber control logic. This interdependence means that a software-level cyber defense lockdown can instantly trigger multi-million-dollar SLA penalties for tenants, even if the electrical and cooling systems remain perfectly healthy. When physical failures do occur, they rarely stay isolated. An electrical fault in a battery room can propagate into a lithium-ion thermal runaway, which then disables mechanical cooling systems, eventually causing a total loss of the IT load. This paper proposes an integrated actuarial framework to account for these cascades. This is a technical shift away from treating fire, network, and power risks as independent variables. Closing the capacity gap requires a pricing model built from the ground up using physics, thermodynamics, and the mathematical statistics of extremes. This single-line wireframe for a Tier 4 AI campus is engineered to hit an availability target of 99.995%. The 2N topology features 2 completely independent powertrains, labeled A and B, each with its own utility feed and UPS room, ensuring complete physical redundancy. The underwriter's challenge is converting this static engineering schematic into a dynamic probability of failure. This chart displays a continuous time Markov chain, allowing us to model the facility across different operating states. A healthy facility sits in the OK state. If one powertrain goes down, the system transitions to the degraded state, losing its fault tolerance. The statistical rate of failure, the transition to this red F node, becomes orders of magnitude higher. Solving the transition matrix for these states calculates the baseline Poisson frequency for insurance claims. The frequency is derived from the hardware design, not just historical luck. This mapping ensures that every actuarial claim frequency is anchored to an engineering-verified annual outage rate. Uptime Institute data shows that cooling failures now drive 12% of public outages. The severity of these events is shifting as cooling architectures evolve. Modern AI training racks now consume between 30 and 120 kilowatts of power. This density has pushed hardware beyond the physical limits of air cooling. Operators have moved to liquid immersion, where dielectric fluids sit in direct contact with energized servers. This creates a tight physical coupling, where a single fluid leak becomes an immediate electrical failure. This graph plots the cooling hazard rate against exterior wet bulb temperature, modeling failure probability as an Arrhenius-type hazard. Above the chiller's design temperature, marked by the dashed line, failure probability rises exponentially. Saturated plants face double-digit hazard multipliers. Because of this nonlinearity, a fully Tier 4 site today can drift into Tier 3 effective performance over a decade simply due to shifting local climate conditions. In two-phase immersion systems, the heat removal capacity is governed by the Clausius-Clapeyron relation. Heat is removed by forcing the fluid to undergo a phase change from liquid to vapor. Integrating this level of physical chemistry into the model allows an actuary to treat cooling as a primary, measurable risk factor. This equation defines the severity of data center losses across 2 mathematical regimes. Attritional losses, like single rack burns, form the body of the distribution. These are routine, high-frequency events. Rare, catastrophic events, like site-wide thermal runaways, occupy the tail. These are modeled using a generalized Pareto distribution to capture their extreme financial weight. This occurrence-exceedance probability curve translates heavy-tail math into a practical tool for measuring the likelihood of a maximum site loss. The red dashed line marks the 1 in 200-year level, required by Solvency II, corresponding to a $280 million loss. Standard property models systematically miss this tail risk, leaving insurers and operators exposed to catastrophic losses they haven't adequately reserved for. This integrated equation brings the Markov-derived frequency, thermodynamic hazards, and heavy-tailed severity together to calculate the technical premium. The process begins with the pure premium, which represents the expected cost of annual operational losses. A risk load is added to account for the volatility of routine attritional losses based on their standard deviation. Finally, a catastrophic load is added using the tail value at risk. This layer specifically funds the extreme losses in the tail of the distribution. The paper applies this to an $8 billion campus case study. By summing a $395,000 pure premium with risk loads for both attritional and cataclysmic layers, we reach a total technical premium of $753,000. Dividing that total by the $8 billion asset value results in a pricing rate of 9.4 basis points. This is an engineering-driven result, not a guess based on historical property records. This calculated premium acts as a shadow price. It forces operators to financially account for the specific physical and operational risks of their facility. This diagram maps the macroeconomic consequences that occur when these integrated risks remain uninsurable. A single data center failure propagates physically, disrupting the power utility grid and triggering cascading defaults across global supply chains. The financial impact flows into the reinsurance and capital markets, where concentrated exposures create systemic vulnerability. This creates a feedback loop where insufficient insurance capacity raises the operator's cost of capital. Higher financing costs then make it more difficult to fund necessary risk mitigation upgrades. This market failure currently translates into a 150 basis point spread on construction debt. That spread costs the global economy billions of dollars every year. Addressing this requires syndicating hyperscale risk into capital markets through catastrophe bonds. To function, these bonds require the mathematical rigor of the coupled power thermal cyber framework. Applying these first principles provides the precision necessary to quantify hyperscale risk. It is the prerequisite for accurately pricing the infrastructure that supports global digital services.